Okay, we're actually finishing up our video or our notes on circular motion with this video. Let's take a look at some more specific examples and look at how we can actually use those equations from the last video to calculate things that we might want to know. To warm up, we're just going to start off by sketching the velocity, centripetal acceleration, and centripetal force vectors for the moon in 5 different locations as it goes in its orbit around the Earth. This is very similar to how we started the last video. So I'm going to draw the moon. Let's say that the moon is moving in this direction, so it's moving counterclockwise. We know that the moon moves around the Earth because of the force of gravity between the two objects. So Fc, we know it's really the force of gravity, but remember, Fc is the net force. So we can refer to this as either Fc, or we can also refer to it as Fg. I'm going to refer to it as Fc because that's what we were asked to do. Fc must point in towards the Earth, and AC points in that direction as well. You can take a few minutes and fill this in. I'm going to pick a few more spots and show you the direction of the vectors. This question usually comes up at least once on the Regents, knowing what direction certain vectors are in, whether it's the velocity vector, the centripetal force vector, or the centripetal acceleration vector. This is an easy point if you remember that the centripetal force and centripetal acceleration vectors always point in towards the center of the circle, and velocity points tangent to the circle in the direction of motion. When it's not in one of these cardinal directions, I mean, the pattern still holds. It's just a little bit, it's not even really trickier to draw. It just, looks a little different. But the pattern is still the same. Okay? So, quick refresher, you should always get these questions about the direction correct. All right? Quick, easy thing to realize. If you're not sure why the force or velocity vectors are in those directions, go and take a look at the beginning of the notes again. Okay? The force is towards the center because that's the direction of the force of gravity acting on the moon towards the Earth. The force of gravity is the only force, so therefore it's the net force, which we call the centripetal force when dealing with circular motion. And the net force and acceleration are always in the same direction. The velocity points tangent to that, perpendicular to the other two, at a right angle to them, because the velocity is tangent to the circle. The velocity shows the direction that the object is moving at that instant. Number 2 is a bit of a review. Calculate the force of gravity between the Earth and the moon. We've actually done this exact problem before, but just to refresh your memory, we can't use Fg equals mg because the moon isn't on the Earth, okay? It's too far away for us to consider it on the Earth. So instead what we do is we use Newton's law of gravitation, his universal law of gravitation, to figure out the force between the Earth and the moon, the gravitational force. That's going to be g m1 m2 over r squared. G, if you remember from the reference tables, is 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. M1, let's use the moon. Moon's mass is 7.35 times 10 to the 22nd kilograms. Earth's mass is 5.98 times 10 to the 24th kilograms. And the distance between them, don't forget that you're going to have to square this. Mean distance, Earth to moon, 3.84 times 10 to the 8th meters. We type in our calculator, remember the EE button. Be careful of the denominator, that can be a little tricky sometimes. And we end up with the same answer we got when we did the gravitation unit, 1.99 times 10 to the 20th newtons. Very big force. Number 3 says determine the centripetal acceleration of the moon as it orbits the Earth. Okay, well, centripetal acceleration, I know two equations that involve AC. That's centripetal acceleration. I know AC equals v squared over r, which I don't know how fast the moon is going, so I don't see how that can help us. Besides, we're going to calculate that later on. I also know this equation, FC equals MAC. Well, in this case, FC, the centripetal force, the net force towards the center of the circle, that's just the force of gravity. Gravity is the net force that keeps the moon moving around the Earth. So FC is simply equal to FG in this case. Therefore, FG is equal to MAC. I just solved for FG. 1.99 times 10 to the 20th newtons equals the mass. Well, which mass am I going to pick? Since this is dealing with circular motion, we're going to deal with the object that's actually moving in a circle. That would be the moon, so we use the moon's mass. 7.35 times 10 to the 22nd kilograms times AC. So we divide this by 7.35, 22. And we get that AC is another very low number, 0.0027. And sometimes people are confused, why is that so low? Well, look, we're dividing a very big number by an even bigger number. So it makes sense that it would be low. And what does this mean? Well, centripetal acceleration has to deal with objects that are moving in circular motion. And if you think about an object in circular motion, that means that it's always changing its direction. This is actually showing us, it's telling us something about how the moon is changing its direction. Okay? A bigger centripetal acceleration would mean the moon is changing its direction much more rapidly. If you think about the moon, it makes one orbit around the Earth about once a month. So if we're talking about just on the basis of a second, it's not changing its direction all that much. Okay? What we can do, though, is we can use this centripetal acceleration to calculate the moon's orbital speed. Because we know that AC is equal to v squared over r. AC is 0.0027 meters per second squared. R is the radius of the circle that the object is traveling in. That would just be the distance between the moon and the Earth, which we already had. 3.84 times 10 to the 8th. So this is interesting. We've got a small number times a really big number. We're going to solve for v squared. We're going to end up multiplying these two together and then taking the square root. We've got a very small number times a very big number. Let's see what happens. Okay, don't forget to take the square root. So we basically multiplied both sides by this, and then we took the square root, and we end up with v equals 1,019 meters per second. That is how fast the moon moves in its orbit. Now, to put in context, 1,000 meters per second would be 1 kilometer per second. 1 kilometer is approximately the distance between where Sulphur Springs and Oneida Street kind of meet and Y off, and the blinking light at Pinnacle and Oneida. What did I say? Sulphur Springs and Oneida. Yeah. So where the road forks to take you either to the middle school or the high school, going from there down to the stoplight on Pinnacle at the intersection of Pinnacle and Oneida, that's about 1 kilometer. The moon moves one of those every second. I don't know about you guys, it takes me at least a minute to drive that far, okay? So, very interestingly, the moon is moving really, really fast, but its orbit is so huge that it still takes it a full month to complete one orbit. Very interesting. So it's cool that we can use a mix of gravitation and circular motion to figure out the orbital speed of some objects that are like in space. We could do the same thing for the Earth to figure out the orbital speed of Earth. We won't, but we could. Here's a more typical centripetal force question. Steve ties a 1 kilogram tennis ball, or a 0.1 kilogram tennis ball, to a string and spins a tennis ball around. The ball is spun in a horizontal circular path of radius 0.75 meters. The ball makes one revolution every 0.6 seconds. We're first asked to determine the speed of the ball. Interesting. In order to determine the speed, I would probably need to know how far it moved and in what time. Let's assume that we're dealing with uniform circular motion here so that the speed is constant. If I knew how far it moved and I knew how much time it took, then I could figure out what the speed is. Interestingly, I'm given how much time it takes for the ball to make one revolution. So if I can figure out how far the ball travels in one revolution, I would have the distance. I divide it by 0.6 seconds, I get the speed. The ball's moving in a circle. we know that the radius is 0.75 meters. If the radius is 0.75 meters, in one revolution, does the ball travel along this radius? Is that what we mean by a revolution? No. Revolution means this, going all the way around the circle. There's a name for that. The distance the ball travels in one revolution is the circumference. And we know the equation to calculate the circumference. And if you don't know it, then you go to page 5 of the reference tables, and you go down to your geometry and trigonometry section. You look at circle, C, circumference, equals 2 pi r, where r is the radius. So I can figure out the circumference, d equals c, distance that it travels, is equal to the circumference, which is equal to 2 pi r. So if I want to find the speed of the ball, the average speed, and I do d over t, I can, instead of writing d, I could just write in 2 pi r over t. The average speed is given by the circumference, how far the ball moves to make one revolution, divided by the time that takes. 2 pi, the radius is 0.75 meters, and in order to go around this circumference, it takes 0.6 seconds. So we have 2 times pi times 0.75. We divide by 0.6. And we see that this ball has an average speed of 7.85 meters per second. Okay? Ball's actually moving pretty fast. Now, based on this, I can calculate the centripetal acceleration of the ball, because I know that AC equals v squared over r. I have a velocity of 7.85 meters per second, and r is simply 0.75 meters from before. Oh, I have to square that. Oof, that would have been bad. So I square this, I divide, oh dear. Let's back up. 2 times pi times 0.75 divided by 0.6. Okay, we're going to square this and then divide by 0.75. We end up with a centripetal acceleration of 82.25 meters per second squared. And again, that doesn't mean that the ball is speeding up or slowing down. That is showing us how rapidly the ball is actually changing direction. Okay? The acceleration here has to deal with changing direction. Does not necessarily have to deal with speeding up or slowing down. Once I have AC, what is the centripetal force acting on the tennis ball, and what force contributes to the centripetal force? Well, FC is very easy to calculate. FC equals MAC. The mass of the ball is 0.1 kilograms. Multiplied by the centripetal acceleration, 82.25 meters per second squared. The centripetal force that causes the ball, that acts on the ball as it accelerates around the circle, is 8.225, I should say, actually, or 8.22. 8.22 newtons. Now, that's the force that what this means, that's the force that this ball would require to move around this circle at this rate, at this speed. What force is providing that? Well, what force is causing the ball to move in a circle? The ball is tied to a string, and someone is holding onto the string and spinning it around. Therefore, the centripetal force in this case is T. It's the tension. Okay? So remember, we can determine what force is causing the what force is causing the circular motion. That's what we mean by this. When we say what force contributes to centripetal force, what force is causing the circular motion in the first place? Okay, a couple more questions. 6. A 1,000 kilogram car moving at 15 meters per second drives around a circular curve. The curve's radius is 10 meters. What is the centripetal acceleration of the car? I could use FC equals MAC, because I have the mass, but I don't know the centripetal force. Matter of fact, that's what I'm looking for in B. I also have this equation. AC equals V squared over R. The speed is 15 meters per second squared over a 10 meter radius. 15 squared divided by 10 is 22.5 meters per second squared. That is what the centripetal acceleration is equal to. And again, based on that, I can find the centripetal force. The mass of the car is 1,000 kilograms. AC is 22.5 meters per second squared. So FC must be 22,500 newtons. Okay, and what force contributes to this centripetal force? What force causes or allows the car to make that turn? We discussed this in the first video. If you're on a very icy surface, you can't go around turns. You'll slide to the outside of the turns. What that tells us is that FC in this case is equal to FF. It is the force of friction that allows the car to turn like this. Question number 7 says, sketch a graph of what AC versus V would look like. Again, just to remind you, let's take a look at that equation. AC equals V squared over R. Now I want you to think about this. If we double what the velocity is, then that doubled velocity would end up getting squared. And what happens when we double something and then square it? It ends up being 4 times as big. If we were to triple the velocity, we would have to triple that extra factor of 3, or excuse me, we'd have to square that extra factor of 3, and that would end up being 9 times as much. 3 squared is 9. If we quadruple the velocity, we end up squaring that extra quadruple. 4 squared is 16. So you can see that even as the factor that you change V by increases linearly, AC increases parabolically. It increases as the square of the velocity increases. So anytime you're graphing something versus a squared, or almost any time, okay, it's on top and it's squared, that means we're going to get a parabolic curve like this, okay? As V increases, AC increases, but at an increasing rate as we change V. The last question is some more algebra practice. An object moves in a circle of radius r with a speed v, giving a centripetal acceleration of ac. What would the new ac be if, and then we have all these changes. Now you can do these in your head if you want. You can write them down. You can come up with numbers, and you can make up your own numbers and see how they change. I'm going to do the algebraic method. Here's our original AC. What happens if V doubles? So I'm going to write AC, and I'm going to put A, since this is problem A, equals VA squared over R. VA is just 2 of the original V, 2V. Remember, I put the exponent outside the parentheses, R, which is 4V squared over R, when I square that inside, which is 4 AC. That's my answer. Okay, what if R doubles? So ACB equals V squared over, let's see, RB, which is V squared over 2R, because R is doubling. RB, the R in question B, is 2 times the original. V squared over R is my original, so I have 1/2 AC. What happens if both V and R double? I'm going to do AC for problem C. Means that we have VC squared over RC. 2 times the original velocity squared over 2 times the original radius gives us 4V squared over 2R. 4 over 2 is just 2. V squared over R is our original. We end up with 2 AC. So sometimes people are tempted to say, oh, the changes balance out because you're changing something on top and on the bottom. That's true, but look at the exponent on top. That's going to make doubling the speed. It's going to end up with an effect that's 4 times as big. What happens if V is cut in half? Well, let's see. That would be 1/2 of the original V squared over R. If I square 1/2, I get 1/4. So I end up with 1/4 times V squared over R, which is 1/4 of the original, 1/4 of AC. If a fraction's on top of another fraction, I can just move it off and down to the side. If it's on the bottom of a fraction, then I move it off to the side, but I have to take the inverse. What happens if r is cut in half? We're going to see that example right now. ACE equals v squared over RE. V squared over 1/2 r. Okay, 1/2 of the original r. Remember, so in some of the equations we've looked at, like the gravitation equation, r is squared. This time, for centripetal acceleration, it is not. So I have a fraction in the denominator of a fraction. I can move it out to the front, but I have to take the reciprocal because it's in the denominator. Reciprocal of 1/2 is 2, so I end up with 2 v squared over r, which means if r is cut in half, we have 2 AC. The centripetal acceleration is twice as much if the velocity stays the same. And that makes sense because if something has a smaller radius and it's still moving at the same speed, it's doing a lot more turning. Okay, if the radius of its path, of its orbit, is smaller, it's doing a lot more turning. If the velocity is cut in half, it's not turning quite as rapidly. It makes sense that AC goes down. Okay, and it makes sense for AC to go up if the speed decreases. It makes sense for AC to go down if R increases. V increases here. I think I might have misspoke. And finally, we have another compound one. What if V triples and R doubles? If V triples, we're now dealing with 3 times the original V. If R doubles, we're dealing with 2R. 3V squared is going to give us 9V squared over 2R, which means AC is 9/2 of the original. In other words, it's bigger. Okay, so there's a little bit more practice with some of these questions where you have to manipulate algebra. That's it for circular motion. The next set of notes that we're going to do together will be on our momentum or impulse and momentum unit. Okay, I will see you later for those.